Hey there. Some time ago, I received a couple of questions from different individuals about solving partial differential equations using the finite difference method in Python. One of them was on extending the video we've already done for the one-dimensional case. We did a one-dimensional diffusion problem, transforming the PDE into a system of ordinary differential equations with some algebraic constraints on them. So this individual was interested in doing the same thing in 2 dimensions. Now his project was for school, and he had to build everything from scratch, all the matrix code, matrix representation, and to do this project in C++. So we're not going to do that in this video. We're just going to basically brute force it and show you how to do all the bookkeeping that's involved. And maybe in a subsequent video we'll go on to show you a more computationally efficient way of doing this. So as you'll see, when we actually run the code, it works, but it's not going to run particularly quickly. So let us just jump into a notebook. We'll quickly review the 1D problem and then set up the 2D problem. So let's go. So just a quick review of the one-dimensional case here. We have this partial differential equation, the diffusion equation here. So the time derivative of temperature is proportional to the second spatial derivative of temperature here, and I came up with these boundary conditions. So at the right-hand boundary, this would be point N on this diagram here. We have the temperature fixed at 30. At the left-hand boundary, we have the temperature fixed at 0 degrees, and everywhere in between is 20, and we wish to know the evolution of the temperature as a function of both space and time. So to solve this numerically, we first approximate the second spatial derivative, the spatial component of this equation, as a finite difference equation that's shown here. And that transforms this partial differential equation into a system of ordinary differential equations with 2 algebraic boundary condition constraints here, and that's shown in this this list of equations. And then we solve it we generate a loop using the Assimilow package for differential algebraic equations, and we get a nice solution. After a long time, you get this linear function. And then later on, we went out to develop a matrix solution. We're not going to do this for the 2D case today. We will probably do it at some future date. But so let us switch over to a new notebook for a 2D problem and set up our imports. For our imports, we're going to do matplotlib just to do some visualization stuff. And we're going to use the Assimilow package to solve our system of differential algebraic equations. And I'm probably going to just time how long these solutions take to run with the time package. So here is the problem kind of written out in a sentence form. Let me come up with a diagram here just to explain things a little more visually. And schematically, our problem looks like this. This is at time equal to 0. The internal of our square is at 30 degrees. And the boundaries are held at fixed temperature 5 on the top and bottom here, and 0 on the left and right sides here. And these remain constant in time while the internal temperature is going to fluctuate. So just as in the 1D problem, we need to discretize this problem, and I'm going to plot out here how we're going to go about doing that. Oh, and I should notice for the sake of this problem, I'm reversing the direction of the y-axis, so y increases as it goes down. That's not going to cause an issue in this problem, but you might want to be careful doing that with other types of problems. So here's the grid we're going to use, and here I'm plotting the index rather than the actual y value. So this would be y equals 0, y equals 1, and I have 6 points here. It's going from 0 to 1, so we have each increment here is the index of our discretization. So right away we have a little bit of an issue in that we're dealing with a square grid here. And our differential equation solver wants things in the form like this. So our left-hand side would be a column vector here. And this is our equations on this side. So we have to kind of reorganize this to produce that type of effect. So when we build out our equations, our algebraic and differential equations, the way I'm going to do that is I'm going to start at the left-hand column, and I'm going to stack all these on top of each other. So the zeroth element of our column vector is going to be this point, the first element this point, all the way down to element 5 in this example, and then element 6 would be this point here. So what would be point 0, 1 on this matrix type representation is going to become point 6 down here. Likewise, this is going to be point, what are we, 1, 2, 3, 4, 5, 6, 7, 8, 6, 7, 8, 9, 10. That would be 11, and this would be point 12, and so on. So we're just going to have to do some sort of mental mapping and kind of, well, actually in code, we're going to have to code out that mapping. And I'll do it down here. I will make this, let me type out the representation of our spatial derivatives. So our spatial derivatives here are going to be approximated by this difference formula here. So you can see that we have in the x direction here, we're going to couple across these columns here. So this is why that bookkeeping is really important to get correct. So I made a couple little alterations here to the plot, and I added in this equation, and this is going to be the mapping of our indices here. So I is going to be the row number, j is the column number, and if there are capital M rows, for any ij, we're going to map to this index here. This will be the index of our vector in the that goes into the differential equation solver. So again, just as I said before, we have coupling in the x, coupling in the y directions, and if you read the literature on this, I'll talk about moving a stencil around your grid. So that's kind of shown here by this this cross. So for any point, we're going to move this point, move this stencil to a given point, and that's going to give us the indices that we need to build our differential equation. So we'll start up here. Actually, we don't need to start at the edge because we already know what the boundaries are. So we'll start here. We'll just kind of go down, 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 using this equation to figure out where our index values are, and that's how we're going to do it. So down here, let's actually start coding up this problem. So just as before, we need to kind of wrap this in a class. Well, we don't need to, but it's just easiest to wrap this in a class, and let's just call it Diffusion, and we'll do everything within the constructor init. So I am going to set the grid to be a square grid again. I'm going to set M, the number of rows, to be 21. So in my example here, there were 6 rows. Now I have 21 rows for a little bit more resolution. N is going to be equal to M just for simplicity's sake. I'm going to define my X values and Y values. And the grid spacing is just going to be given by this here. So I'm taking the difference between the X values and the first element of that vector. And all elements are the same since the grid is equally spaced. So T0 is going to be our initial temperature. So that's the initial temperature of the grid. So I set all of the, it's a square array, n by m, and n and m are equal, so that they're square. They're all 38 degrees, and then I'm going to set the left and right hand side to 0 and the top and bottom to 5. And I need to handle the case of the corners here. Is this a 5 or a 0? I'm just going to take it to be a 5. So the sides are zeros except for the upper corner and lower corner, and those are going to be 5s. So those are my initial conditions. What to do next? This is in a square matrix form, and we need to put it into a column form. The question is, do I want to write a function to do this indexing here, or type it out by hand every time? Let me write a separate function down here. So define, we'll call the function return index, return index column, and this will take I and j as an argument and spit out the value given by this formula here. Let me just run this block just to make sure there are no typos as of yet, and of course there are. What is the issue here? An indentation issue. There we go. So now we can do our mapping from this square matrix to a column vector. T is going to be our column vector, and we're just going to iterate over that matrix and use this transformation equation to get from matrix indices into column indices here. So let us now define our system of equations here. So let's call this let's go equations. It's going to need self, it's going to need time little t, it's going to need temperature capital T, and it's going to take a value T prime. It needs the derivative of the temperature, and we also need a vector of called SW for switches, which is used for event detection, that type of thing, which we really don't need here, but we need to pass it in anyways. And we need a residual vector. I always like to initialize it first. Let's just set it all equal to 0. So np.zeros, and it's going to be the same size as t. So that's that. Let's make it the same shape as t.shape. And now let's do the differential equations here. So we're going to iterate over this grid, applying this difference formula, again using our transformation equation down here. So here is our differential equation in a differencing format. So I'm just iterating over the grid, just as I said before. I'm using a mixture of this function return index column and manually entering it in here, just to keep things clear in my head, because we have to move the i's and j's around a bit. So sloppy, but whatever. So that's that. Let us set up the boundary conditions now. So we have to kind of go over the sides of the grids and set the temperatures appropriately. So let me come down here and do that. So here we are, our boundary conditions, setting temperature equal to either 0 here or 5 here for the appropriate side. Let me just run this cell again to make sure everything seems cool. It does. So now we need to come up here and actually call the solver. Now I've gone over a Similo and IDA solver in other videos, so I'm not going to dwell on that. I'm just going to do it real quick. We're going to need to pass into the solver T prime here. And we're going to assume that's all zeros to begin with. We need to set the switch variable, so we don't really need it. So I'm just going to set it to all false. So I'm going to call it SW0, and that's going to be equal to, let's just call it SW, so don't get confused. That's just going to be equal to false, and it needs to be false for every value in t. So t.size, so that's just an array of 21, I don't know how long that is. 21 squared, basically, false values. So that's that. We need to set up a variable called algebraic variables that'll tell which of these down here are algebraic and which are differential. So let me do that. So here's our algebraic variables. I'm just setting them all to true and then setting the appropriate ones to false. We've gone over the assimilar solver, as I said before, so I'm not going to dwell on this. So we now need to just create a model and call the solver. So again, create a model. We set the internal, the simulation type to IDA as the actual solver that we're calling. We set our algebraic variables, calculate the initial conditions, and just call the solver, and we're calculating it at time equal to 10. So hopefully there are no typos in any of this. Let me run the cell. So far so good. Let's come down here and actually run it. So let's see if it actually works. I want to time it with these statements here. I'm going to create the diffusion object, set it equal to sol, and then pull out the solution, the time, and the temperature from the set variables there. So let's run it. There is an issue. I think it's a typo when I'm setting t dot. I use t dot size to do the here. It should be t dot, not t minus. So run. Still an issue. Equations, it's having a problem with the equation. Oh, I called this. I bet you I called this. I called this equations and I called this equation. So let's put an S at the end here. Run. User function is failing. I never even returned this variable, did I? The residual. Return res. There we go. And we get our solutions, and we see that this code is not particularly speedy. It takes 50 seconds basically to solve a very simple problem. So that's why you want to use sparse matrix methods, which we'll do in a future video. But let's just plot out the solutions. So I'm going to plot out the solution at time 10. The way this is stored, each row is a time slice. So the last row is the final time, and then we need to reshape it back into a square matrix. So there is our temperature profile, which looks reasonable. And just as a sanity check, I ran the same problem through MATLAB. MATLAB has a finite element solver with it, PDE toolbox. And so I plotted the solution from that. I took a slice basically down the middle. It's not exactly down the middle because the grid isn't exactly even, but it's very close to it. And I plotted our solution down the middle too, and you can see that the two basically match perfectly. So good job out of us, and I think that will do it for this video. I think I will clean up this notebook before uploading it to GitHub, and cool. So pretty simple, at least conceptually, as I've said throughout the video and in the intro. It's just a lot of bookkeeping. And in a subsequent video, I want to see if we could use sparse matrices to solve this problem. I haven't really tried to do this with a simulo at this point, so this is going to be a new thing for me. So if it works, I'll show you exactly how I put it together. So until next time, see ya.